I thought that for my talk, I would try to give you a little bit of the feel for some of the issues that we were facing over the 10 years leading up to the discovery. And in fact, I'm going to use mostly graphics from the original overhead transparencies that we were using over those years. So they're not the most beautiful of our modern day graphics, but I hope they'll give you a bit of the texture of what was going on during that period. And I'll try and end a little bit with some of the more sort of human side of the story after I go through a little bit of the sort of science issues that we faced as we went along. The whole question, of course, that we were all working on is something which I think you can imagine that these were questions that the very first humans could have walked out of their caves at night and found themselves looking up at the starry sky and wondering, do we live in a universe that goes on forever in space and will it last forever in time? And I think it almost defines what it might be to have found the very first humans that they could ask such questions. And it's wonderful that we found ourselves just in this past century with Einstein's theory of relativity and Hubble's and Slipher's measurement of the expansion of the universe in a position to make that question into a more rigorous, measurable scientific question. And that it boiled down to a simple matter for the fate of the universe of whether it's going to expand forever or someday turn over and collapse, of just looking back into the past and seeing what the universe was doing before. How much has it been slowing in the past? And of course, we were amazingly fortunate that there was a simple way to answer that question, to make that measurement using these supernovae. And here, of course, the idea that the brightness of the supernova can tell you how far away they are, and hence how far back in time you're looking. And that the colors of the spectra of the supernova, where the supernova are primarily blue when they explode, if you were able to see them nearby without being blown up, as the universe expands, the light's traveling to you and the photons are getting stretched from blue to red. So by the time we see them today, they've been red shifted. And how much they've been shifted to the red exactly is a measure of how much the universe has stretched since the time of that explosion. So if you start plotting these points for a supernova on a plot like this, you could look back in time to see what the history of the expansion of the universe was. So I think it's just it's amazing that we lived at a time that you could ask this very philosophical question with this very simple and perhaps ideally explainable measurement. So that was that was part of where we began the story. And of course, we knew that this kind of measurement could be done since the early 1930s, when the first astronomers studying supernova had considered the matter and had even proposed this measurement. But for most of the next 50 years, we had this problem that the supernova that were being looked at actually had a pretty broad range of brightnesses at peak. So they really sort of spread over the whole map of brightnesses, and it wasn't going to be possible to make this very detailed measurement with the supernova, at least as far as we could tell during that period. I think that what got us into this game in the mid-1980s were really two new developments. So let me describe those two developments. The first one was that in the mid-80s, there were a series of papers that came out from the supernova community that were starting to point out that there was a sub-classification of supernova, the type 1A, as we now call it, supernova, which appeared to be much more standard than just the general run-of-the-mill classification, general supernova that you had available. And for example, one of the papers by Nino Panagia in 1985 showed a plot like this, where you could see that the range, the spread of the brightnesses at peak of a type 1A supernova, and these were supernovae found in the elliptical-hosted galaxies. These had a much narrower distribution than the general supernova that you'd find in spirals. These were the ones that turned out to be type 1As, actually. And so this was part one of what got us involved. Part two was a technological development, or a series of technological developments. There were new detectors available, the CCD detectors, which in fact won the Nobel Prize just 2 years ago. And these detectors made it possible to make much more sensitive measurements, but also to read them directly into a computer. You all, of course, nowadays will have CCD cameras in your cell phones and video cameras. And now you could read it into a computer, and the computers were now just becoming fast enough that you could analyze images at this stage. So these technological developments actually led Nobel laureate Luis Alvarez to suggest to Rich Mower. So Rich Mower was Luis Alvarez's student Louis was his advisor for a PhD, and Rich Mower was my advisor for a PhD. And Louis suggested to Rich that it was time to try to do a robotic supernova search in the style of something that Sterling Colgate had started working on a number of years earlier, but before the technology was really ready. And now it seemed like it was time to do this work. And in fact, Rich developed in this amazing research group that I joined as a graduate student, which was doing so many surprising, unusual projects. One of them was the Berkeley Automated Supernova Search, which became a very successful project, found some 20 supernovae. It was the first of its kind. And I was working in the group with Carl Pennypacker, as Carl was one of the postdocs. I was a young student at the time. And so this is where we sort of cut our teeth on supernova work, and also on doing the analyses using the computers to do this image analysis that would allow you to subtract an image of a galaxy from an image of a galaxy with a supernova and be left with just the supernova. Now, it was while we were working on that project that Carl Pennypacker and I got together, and we started thinking, well, seeing what we're seeing now about these type 1a supernova, isn't it really time to try to do the much more distant search for supernova, and perhaps do the work that Bada and Zwicky back in the 30s might have liked to have done to see whether we could measure the slowing of the expansion of the universe? And at the time, we felt that we had the ingredients to do it, but we were very aware that there were a lot of hurdles we were going to have to cross to make this work. And so it was not a trivial task to do this. And the early reviewers and critics of the program, I think, were on strong footing when they would point out that there were many, many problems that we would have to address to make this happen. So I thought today I would show you, walk through a few of these and show you what happened and how we ended up addressing these different problems. And they ranged from problems like, can you find the supernova far enough? Can they find them early enough? Because you need to measure them as they peaked, since that was what was standard for the supernova. Can they be recognized as type 1a at great distances? Are you going to be able to compare the distant ones to nearby ones? Are they standard enough? In other words, will they act as a good enough standard candle? And will they stay a good standard candle as you go back in time? So this was sort of the range of problems. And let me just begin with the first, just this problem of whether you can find them and catch them early enough before they peaked. Now, I've been telling you how wonderful supernovae are and what a great tool they could be for this purpose. But when it comes down to it, if you have any other option for anything else you can do your research with, don't use supernova. They're a real pain in the neck. They only explode a couple of times per millennium. There's only so long you want to hang around as a grad student. They don't give you any warning that they're going to explode, so you can't apply for a telescope time because there may be a supernova exploding in the next 500 years. And they rise in just a few weeks, and they fade away in a few months, so you can't come back afterwards and go and study the supernova. So it's just not a great tool if you could do anything differently. In fact, at the time, another project began. This was a Danish group led by Norgard Nielsen, who I actually just met yesterday for the first time. After all these years, I've been wanting to meet him. And they were able to show us that there were, in fact, supernovae out there to be found. They found one supernova in the distances that you needed to reach. But they also highlighted how difficult it was going to be since they did this intensive project for several years and were able to find one type 1a supernova, and it was already past maximum at the time of discovery. So this was still a bit of fodder for the critics at the time of the project. And we realized that we needed a way to get a much larger number of supernovae into the game. And what Carl and I ended up proposing was the idea of using a very wide field, a rather novel wide field camera, which would you mounted here on the 4-meter telescope in the Anglo-Australian telescope at the time. And this allowed you to not just observe one galaxy at a time, as we've done with the low redshift robotic search, but now hundreds of galaxies from a fairly broad patch of sky on this little CCD chip. The biggest we could get at the time was 1,000 by 1,000, and that was considered to be really big. And of course, you have much more in your cell phone today. These hundreds of galaxies now, we could get almost 10 to 20 times more in a single image than the Danish group was able to get in a cluster that they would be observing at the time. So that meant that now you could start finding a reasonable number of supernovae, because now looking at hundreds and hundreds and ideally thousands over the course of a night, you could guarantee that there'd be some supernova that you would find. And this was the beginning of this effort. The images looked like this that came from that first camera. What you want to focus on are all these little faint specks here in the background. Those are the distant galaxies in which we needed to find a fainter speck of light that was the supernova. We would subtract off images taken earlier and try and line them up. And then the residual would be the supernova. And of course, we had to do this not with transparencies, but with computer software to be sensitive enough to find these distant supernovae. And so a lot of this work in the early days was developing the computer software to do these subtractions right, so the computer could point out to you where the supernova would lie in that kind of image. And this actually started to work, except for the fact that you couldn't still predict when you would find your supernova discovery, and we had a chicken and egg problem, because we would need the largest telescopes in the world to confirm that this was in fact the Type 1a supernova we had found, but you actually weren't able to schedule a supernova, schedule a telescope to follow that supernova, because you hadn't yet proven that you were finding Type 1a supernova. And of course, here's where you got hit by the fact they were random, that you couldn't actually schedule that follow-up time. Now, there was an interesting comment written by Mario Amui when he was describing the lower redshift work with the Calan-Tololo supernova survey that you heard about, which is that they were pointing out that this unfortunate problem that the appearance of the supernova is not predictable, and as a consequence of this, we cannot schedule the follow-up observations a priori. And so generally, we have to rely on someone else's telescope time, which makes the execution of the problem somewhat difficult. Now, somewhat difficult at low redshift meant that you would be begging and borrowing time, and we had a lot of experience with this from our earlier supernova work, where you call people up at the observatory. They were really not looking forward to hearing the name Saul Perlmutter on the phone after a little while. And of course, the idea of doing this at high redshift was almost prohibitive, because now you needed just the rare few biggest telescopes in the world, and you would be using a substantial amount of time. And so this did not make for a good project if that's the way you had to do it, by borrowing time from other people's telescopes time. So what we ended up developing was a new timing strategy, which I think made this all possible for us. The idea was that you would clump all of your observations on these sides of the new moon. So first, you'd observe right after a new moon and collect all your data of these hundreds and thousands of galaxies. Come back a few weeks later, just before the next new moon, and collect the observations again. And now when you did the subtractions and you found your new supernova, this 2.5-week gap would not be enough time for the supernova to brighten to peak. And so all the supernovae you would find there would be on their way up, so that now you'd be catching them before peak. And you would have timed it in such a way that you were making all the observations to find them just before the new moon, which is the perfect time to schedule your follow-up spectroscopy and then to continue your follow-up photometry to watch it brighten and fade away. And now you could request time to schedule the follow-up of the supernova, and this became a much more systematic approach, and it started to work. In fact, the very first time that we were going full speed ahead with this, what we called batch technique of discovery, I called up the International Astronomical Union telegram service to warn them ahead of time. These are the telegrams that get sent out to observers around the world when a new transient object is available that they might want to study. And they were very careful about what they would allow into the telegram, so I figured I'd better check with them to make sure they were able and willing to take the next batch of supernova that we might find. And of course, they laughed because I was saying that we were going to find half a dozen supernova on a certain date coming up. Nobody had ever predicted a supernova discovery before, and certainly nobody, I don't think there are very many cases where more than one was found at a time. And here I was saying, half a dozen on, what was November the 14th or whatever it was at the time. And, but sure enough, the telegram came out with more than half a dozen supernova, and there was telegram after telegram then every semester for the next several years. We would go out and find batches of supernova, and in fact the two teams were now in this business doing this batch approach. All right, so that was how we were addressing this first problem. The second problem was, once you found a supernova, would they be so faint that you wouldn't be able to recognize that they were a type 1a supernova? And also, how would you compare the brightness of a supernova at high redshift to one that was relatively nearby at low redshift? So here, in fact, when you first look at the data for the very first time for these very, very distant supernova, even if you were used to what nearby supernova looked like, it really did look like noise. And just this up and down was just all over the map. What we realized, though, was that the supernova features that we were interested in, the way you recognize a supernova in a spectrum like this, is due to these very broad lines that are spread out over wavelength because the supernova explosion has smeared out all the wavelengths of the light. And we're not interested in all these sharp little features that stick up. Those you could cut out or smooth over. And when you smooth the results, you can now compare it to what a low redshift supernova would look like, that you then start to redshift to see where the redshift matches. And when you did get the match, you now actually saw that you not only knew the redshift, but you really were able to recognize the features of a type 1a supernova. And now we actually were able to say that those things out there were the type 1a supernova that we've been studying closer in. There was another problem that was pointed out about this shifting of the spectrum, which is, let me just switch here, which is that the supernova that when you're observing the brightness of the supernova to get that peak brightness that you're going to calibrate your distances with, the light is mostly coming in the blue parts of the spectrum, and so therefore you usually observe them with a blue filter. It's called the B filter here. But when you are at high redshift, the spectrum's been shifted over, and now that blue filter is just looking at this little bit of the tail of this spectrum of the supernova. And so you're going to confuse the dimming of the supernova just because of the distance with the dimming because you're looking at this very faint ultraviolet tail of this spectrum. And of course, this is something that was understood and known. There was a nice paper by Bruno Leibengut at the time where he actually calculated what the K correction would have to be to correct for the difference between this peak part of the spectrum and this tail part of the spectrum. And at the time, that measurement of that correction had an uncertainty on it, and the uncertainty was huge. We really were not going to be able to make a very precise measurement with the uncertainty that we had for, on this correction. And this was one of the real challenges at the time. What we realized, though, when we found our first supernova at redshift 0.458 was that there's actually a better way to make this comparison of the distant supernova and the nearby supernova. And that's to measure the distant supernova in the red part of the spectrum using a different filter, the R filter for red. And there you can see that the light that's coming through in the red filter is almost the same part of the spectrum at high redshift as you see through the blue filter at low redshift. And so the correction becomes very tiny, and the error bars are now much tinier. The uncertainty is is not a big problem. So we now were able to address this concern that came up. All right, so those were these two items. Then next was the fundamental question, are the supernova really standard enough to do this job? Now, after Nino Panagia's paper that I mentioned and the others from the early 80s, a lot more work went into it. There was, in particular, a series of papers by Bruno Leibengut and Gustav Taman that I felt were very influential, where they started studying a series of light curves, these brightening and fading light curves of the type 1a supernova, and they were showing how similar the supernova were. And I thought that was very important. There's also some very interesting work going on by David Branch's group in Oklahoma. And that work, this is actually from a data set from a later paper, but from even the early 90s, there was work where they were pointing out that if you plotted the redshift against the brightness, the magnitude of the supernova, that there were a number of the supernovae that would lie on this very straight line that you would expect if they were really good standard candles. But there, of course, are these guys down here, which would ruin the whole measurement if you had to include them in the picture. And what David Branch and his group pointed out was that those other supernovae actually could be reasonably well distinguished just by measuring the color of the supernova. If you could just find the redder supernova, and these all turned out to be redder, you could throw them out and be left with just the ones that were the very nice standard candles of the time. This was probably because the redder ones, some of them would have the light diminished by looking through dust. And some of them, we thought, could be just intrinsically slightly fainter, unusual type 1a supernova, and their unusualness could be recognized because they were red as well. So this was actually what we saw in the early stages as the route that we would take to getting a good standard candle to work with. And the dispersion of around this line, this spread around this line, was actually reasonably tight. That observed dispersion of nearby type 1a peak brightnesses went from some 40 to 50% dispersion down to something like 30% when you cut out the red supernova. And that 30% was an observed dispersion. For all we knew, it was all just due to the measurement error, and that the supernova themselves were even better than that. And that's what turned out to be the case when the beautiful data set that the Kalan-Tololo supernova research found was added into the mix. So this was the work of Mario Amui, Jose Maza, Mark Phillips, Nick Sunsef, and company, where they went out and they found a set of supernova in a nearby Hubble flow that was a more beautiful set than I think that any of us had ever seen before. Using that data set, you could use the same color selection, just cut out the red supernova, and now the observed dispersion goes down to some 18% in brightness. That's 9% in distance. And so now we had what looked like a really usable standard candle at this stage to go ahead with. Now, of course, that was improved by Mark Phillips within the next year. He had already shown that the decline rate, the speed in which the supernova falls off, tells you how bright that supernova is going to be. There was this beautiful statistical work of Adam Rees, Bill Press, and Bob Kirshner, where they used this other technique to essentially capture the same effect. And we were using a third approach, where we were stretching and compressing the time scale of the supernova template. And how much and how little you would have to stretch that time scale was another way to predict the brightness of the supernova. And with that one parameter, the stretch of the time scale of the supernova, you could bring all of this range of Kalan-Tololo supernova into alignment and make a beautiful single template of a supernova light curve. So this is how we were able, at that point, to even improve the standard candle, and that's what I think the groups were all using as their methods. Now, the other issue, there are other approaches to handling the redder, dustier supernova than just throwing them out. You could correct each one of them one at a time for that color, and we were using that as one of the approaches at the time. But we also felt that given the quality of the data that was available for both groups at that stage, that we were arguing that you actually needed a very strong cross-check, and we were using the composite histograms of all of the colors of the supernova at low redshift compared to high redshift to make sure that the general distribution of colors and dust at high redshift was not greatly different from that at low redshift. And so that was another approach that we were taking then. All right, so then fourth item here was, isn't it possible that the supernova would change over time? How do we know that they're still the same as you go back billions of years and that the standard candle remains a standard candle? Now, here we had proposed in some of the early papers an approach, and I'm going to show you some pictures from a later paper, where you would look at the supernova found in one particular kind of galaxy, the elliptical host galaxies, and make your measurement of the expansion history of the universe just using those supernova. Or you could also make the same measurement using supernova found in these spiral galaxies, either the early spirals or the late spirals. And if each of these separate measurements agreed with each other, that would give you confidence that you weren't seeing just an evolutionary effect that was distorting your results. Because each of these different environments has a very different history, a very different evolutionary history. And so therefore, it would be really surprising if you got the same result in all of these environments, and yet it was just due to some distorted evolution effect. All right. Even with these 4 in hand, it was in the early 90s that we realized that there was actually one additional problem that we had to deal with. It was a problem of a slightly different character, and this is that in the early 90s, there was starting to be discussion that maybe we should be looking at Einstein's cosmological constant again in the picture. And that sort of threw a whole monkey wrench into the measurement in our minds at the time, because we realized that the cosmological constant, one of its whole purposes, putting it into cosmological equations, is to counteract the slowing of gravity. It would tend to make the universe speed up, where gravity would tend to make it slow down. And so if you made a measurement of a given supernova, and you thought you were measuring how much the universe was slowing down due to the gravitational attraction of the stuff in the universe, you could be fooled, because it could be that you're seeing less mass in the universe, or more of this lambda, and you wouldn't be able to tell apart which of these was in play. And this is something that Ariel Gubar from Stockholm started to work with me on in the early days when he first joined our group in Berkeley. And in the paper that we put out in our analysis around 1994, we realized that, yes, with a single supernova, that if you measure the brightness, you know that you're on a strip like this in this plane of the cosmological constant density versus the mass density of the universe. So you don't know from one supernova whether you have more lambda and more mass, or less of this cosmological constant lambda and less mass. But you don't have to just work with a single supernova and a single redshift. If we could get a supernova, and these are all hypothetical supernovas still at that time, we didn't yet have one at this distance. If we could work at a much higher redshift, for example, redshift of 1, then that strip rotates. And now it looks more like this. And if you had several supernovae, you could look for the overlap region. And that would tell you that you had this value of the cosmological density, constant density, and this value of the mass density. And of course, you could do it with many more than 2 supernovae. And that was what we proposed to do. And in fact, that's in the end what we ended up using as our way of distinguishing these features. So all those pieces were in play. We set out then to observe batch after batch of supernova, working now these telescopes around the world simultaneously. And in fact, now we were using the Hubble Space Telescope above the world. It turned out that the fact that we were able to predict the date of a supernova explosion was very crucial to being able to use the Hubble Space Telescope. You had to schedule it way in advance. But in fact, we even could predict where roughly in the sky the supernova would be found, because we would find them where we looked. And so we would look, batch right there, and then you could point the Hubble Space Telescope ahead of time in its scheduling to be ready to look at that place in the sky, and then you do the last little tweaking of exactly where to look on that week, once you actually had found the supernova. So we were now in this business of finding batch after batch of supernova, and each semester then, we would add to this histogram of where the redshifts were that we had found supernova at so far. So this was the first batch here in blue. Second batch came in green. Here's the next one in orange that I'm showing you. Eventually, actually, we even got to the point where, they were mostly being followed with the Hubble Space Telescope, but we started to look for those supernova at the extremely high redshifts, the ones that could cross the bands that I showed you before. And we found the first example of a supernova way out in the decelerating part of the distances here at redshift 1.2. And I think that was instrumental in helping to kick off that beautiful work that you heard from Adam Rees in being able to show that deceleration is still in play when you go back far enough in time. Now, these data sets then, we started to plot them in 1997 on the diagrams, the Hubble diagram as it's called. And the first set of supernova, just that we put on, actually pointed to what looked like a higher mass density universe. Once we added the first of the very well-measured high redshift supernova, this is the first example of a Hubble Space Telescope supernova at redshift of 0.84. And at that redshift, you now start to see we're pointing more towards this lower mass universe that actually has some cosmological constant in it. So this was actually getting to be interesting, but of course really became interesting when you threw 42 supernovae onto the plot. 42 is a very auspicious number for those who followed Hitchhiker's Guide to the Galaxy. And with that data set, we were starting to see this, we saw the surprise that you've heard about, this was really what was kicking off the sense that we are living in a universe that's nothing like we expected. If you plot it back on that graph I showed you at the very beginning, the low redshift supernovae are here. The high redshift supernovae that were supposed to tell us which of these decelerating lines we live on and then whether we expand forever or collapse, then missed all of these possible curves. And so apparently we lived in a universe that was slowing and is now accelerating. And of course, that's why we now believe that we live in a universe that could be dominated by dark energy. Modifications of Einstein's theory of general relativity is an alternative possibility. And to be able to distinguish, and of course the theorists have been having a wonderful time writing paper after paper. I think I was estimating that there's roughly been a paper every day since the discovery from a theorist. And if you ask them whether they stand by their theories, almost all of them will say, no, we're really looking back to you, the experimentalists, to give us some more of a guidance on where we should be going on all this. And they come up with these, perhaps the best you can say is they come up with wonderful names. I love Big Rip cosmology and ekperiodic universe, you can barely pronounce. So it's not true that we've been just sitting around. The observers have been working very hard. The supernova story that had some 50 supernovae on it at the time of the discovery, if I turn this plot upside down and backwards, the way the astronomers like to show it, it's now has some 500 supernovae, more than 500 are on that plot from a number of different projects. And so this is a lot of progress has been made, but almost any of those dark energy theories that I showed you would fit into this plot. So we need to even do better than this. And we are now moving ahead with further techniques to make the supernova a much better measurement. And I think we now know how to do that next generation of experiments. We have other techniques available to us, which we did not have in the past. And so over the last 10 years, there's techniques that have been developed where you take the distances between the hot and cold spots that we see in the leftover cosmic microwave background from the Big Bang. That was, of course, the 2006 Nobel Prize. And use those as characteristic distances between where the galaxies will form. And then we look to see where the galaxies did form by observing the sky today and measuring the positions of all the galaxies in the sky. And so you can get the characteristic distance that you find now and compare it to then, and that tells you about the expansion history. And there's an orthogonal approach called weak lensing, where you measure the distortion of distant galaxy shapes using the intervening matter as your gravitational lens that distorts those shapes. And all these techniques together, I think, give us a really good shot at helping the theorists know what part of their range of solutions they should be taking seriously. So at this stage, there are a number of projects that are all going through the review processes, through the recommendations. Several of them have been chosen several times now, so we're really hoping they actually get built soon. Recently, the Euclid was in Europe as one of the space missions. WFIRST is the one that the US is hoping to do. And then there's several on the ground. So I think there's a really good shot that you'll come back here I hope, just a decade or so from now, and we'll actually be able to hear the Nobel lecture from somebody who now can tell us why it is that the universe is accelerating. All right, everything I've been telling you so far, I think, has been making it sound as if the scientific process is a very cut and dried approach where you just identify the problem, you find the answer, and then you go ahead and you make your measurement, and you get the Nobel Prize. But the experience really is completely different. It's this whirlwind of activity and people, and I wish I had 10 years of photographs to show you what we were all doing during that period that could convey some of that, and I don't. So instead, I several years ago had written down, it's sort of a verbal portrait of some of what this looked like and felt like. And so I was going to finish this by reading a little bit of that to you, and I hope that conveys a little bit of what the experience is actually like when we over this 10-year period that we were doing all this. So it all begins with a brainstorming in Berkeley with Carl Pennypacker in 1987 as we first batted around the hardware and software plans for a new high redshift supernova project in Rich Muller's group, which Rich soon embraced. And then the consequence, the Mountaintop Observatory Cafeteria at Cunabarbran, as Carl, I, graduate student Heidi Newberg, and former graduate student Shane Burns got to know our pioneering Australian-based colleagues, Warwick Couch and Brian Boyle, installing and then using our weird crystal ball of a wide field corrector and camera at the AAT 4-meter telescope, which led to our first high redshift, but unconfirmed supernova. And then back in Berkeley, I have this image of Gerson Goldhaber overlaying transparency with negative and positive images of the fields full of galaxies. And this was the image analysis for the days when the computers were down. And I should pause here just to say that we're really very sad that Gerson isn't here today. He died just over a year ago, and he was a warm heart and really sharp eyes of our team, and the host of the collaboration parties. And so he should have been here to celebrate with us. In Australia, we had rain. I think that we had like 2.5 nights of good weather out of 12, and more clouds, and then the sunny relief of La Palma. Where our new Cambridge colleagues, Richard McMahon, working with Mike Irwin, studied the most distant quasars. So we had long nights of debugging a new instrument at La Palma and making tense phone calls to the Isaac Newton telescope while the data was sent to Berkeley for analysis. And then our first official high redshift supernova and a crucial La Palma spectrum from the Herschel telescope, as Richard Ellis has by now joined the team after being one of those Danish group pioneers. By this time, the Europeans had arrived full force in Berkeley. Ariel Gubar from Stockholm kicked it off, developing new analyses with our then grad student Alex Kim, and brainstorming with me about the cosmological measurements. We have a glimpse of Renaud Pin from Paris, assessing the damage and successes at the end of a complex telescope run, the first of the so-called batch discoveries. And this epic ends, in my mind, with a celebratory party at Gerson Goldhaber's in the Berkeley Hills, where we have a bottle of champagne for each of the half-dozen supernova discovered in that batch. Now, the sociology changes a little as we move to mass production, with new outposts at telescopes around the world, typically manned by a lone team member tenuously connected by a stream of email, fax, and phone. So Pilar Ruiz Lapuente and Nick Walton are at La Palma. Chris Lidman is the voice at the VLT in Chile. Brad Schaefer at Kitt Peak. Then larger expeditionary forces head to Cerro Tololo in Chile, where all the supernova discoveries now are generated. And I picture Don Groom and Susanna Destuel on one such trip. Immediately followed by another team of us rushing with a new list of likely supernova to the oxygen-poor mountaintop of the then-new Keck telescope. And I have this memory video clip in my mind of Alex Filipinko, who was then on our team, with our new Cambridge PhD Isabel Hook and I crowding around the computer screen as supernova after supernova proved itself. And at the control center in Berkeley, the graduate students are working round the clock. I picture Matthew Kim and from France, Sébastien Fabreau, in the cramped room full of students, postdocs, and computers, where our former undergraduate intern, Ivan Small, is now presiding over the growing search software. I then imagine the calm of space as the Hubble Space Telescope quietly does its part of the job. But of course, down on Earth, the same flurry of humans, here Andy Fruchter and Nino Panagia, make it possible to use that robot effectively. And then the last act begins with a view of the end-of-night cleanup after another celebratory party. But this time, there are entire cases of bottles of champagne left undrunk. We're lightweights. They're all labeled with the names of the now scores of new supernova to be analyzed. And a fresh relief team of scientists is now on the field at Berkeley. So Rob Knopp, who thinks, types, and programs faster than I talk. Peter Nugent, who's juggling supernova theory and practice, and Greg Aldering is pulling together all the strains of the analysis and the search. And a final push of analysis has all of our Berkeley-based pre-graduate school interns working nights and weekends. It was parallel computing at its finest. First Julia Lee, and then Patricia Castro, Nelson Nunez, and Robert Quimby, all now continuing careers in the field. And finally, we all fall gasping in a metaphorical heap with the surprising discovery about the universe that you just heard about. And all that's just our team. So I think it's pretty clear from all this that the popular image of the lone scientist in the laboratory looks nothing at all like our experience of the science. And science, at least for us, is this extremely social activity, and maybe the most social activity. This particular work was the product of an amazing community of scientists. And between our two teams, in fact, we include a large fraction, but not all, of that community of scientists studying supernova, and just sort of representing the rest of the supernova community that was so important to this work. I show here several of the key players that I mentioned in this talk, with whom it was an honor and a pleasure to work on this. None of this whirlwind of human choreography happens without the constant support of our families and friends, our teachers and mentors, and our staff at the universities, labs, and observatories. And also, in some cases, the really courageous administrators and funders who took risks on things that was not obvious they were going to work. And all these are represented here today by the family and friends who are here. And we all thank you for helping and putting up with all this. But the work is not done. We're looking forward to joining in with the next tag teams of scientists as we delve into the mystery that we are currently calling dark energy. And finally, we are grateful for the Nobel Prize committees and foundation who have found a way to encourage this very human activity of science. So thank you.
Thank you very much. I think we should bring all three laureates on the stage. Thank them for wonderful speeches and for wonderful science. Thank you all for coming. Thank you.